اليوم إن شاء الله نعطوا الشغل والطاقة وننتقلوا بعدها لمحاضرة في خواص المادة. الشغل طبعا يحتمل نفس العملية على قوانين نيوتن. قانون نيوتن اللي خذيناه المحاضرة اللي فاتت كان F تساوي ma، والشغل work طبعا هذه n نيوتن. الشغل يساوي equals to Fx, the force times the distance. That means this is the mass, okay, and this the force m, and create m here. The distance is x. If we multiply F times x, it gives us the work. Okay. Here F is ma, is equal to ma, which is F times x. And we have the equation is v square, v0 square plus 2ax, okay? And now we say v square minus v0 square is equal to 2ax, and from here we say a is equal to v square minus v0 square over 2x. We'll take the a here, okay? Then the work is m v square minus v0 square over 2x times x. That will give us half m v square minus v0 square, or mv square minus half mv0 square, which is the kinetic energy, k minus k0. And here that's we call the this is Newton meter, which is called joule. Okay. Also in here, now we came to the energy, the difference in the kinetic energy from this place here, which is 0, and this place here is 1, or the final, and then now what this the work is this one. Okay, let's talk about also the last lecture. I explained for the Newton's law, okay, in here. This is m, hang to m1, say, m3, and say here, m2, and I said the movement of this way, okay? And here, this is the m3g, this is the t2, and here t2, and we say t1, and t1, and m2g. Now we don't deal with the direction of plus y and minus y, okay? We deal with the direction of movement. If we say the movement is this way, and this case here, this is the positive because A is going this way. The movement is this way. This is the positive, and this is the negative. And here, this here is T2 will be positive, and this is negative. This will be positive because A is this way, the movement is this way, and this is the negative. Okay, this is this point because many students, they confused with this. They put this positive as Y positive, and this is negative by Y negative. No, this is the all. I told you the forces, the negative forces, always opposite to the direction. Like we said, the frictional force, spring force, and so on. All negative because they are opposite to the direction of movement. Okay? Now this is negative because it's opposite the direction of movement downward, and this is upward. This is the negative. Please be careful with this. Okay? We'll talk also about work we say is delta K. What is the K? This is here, delta K. Okay. If we say, for example, you have there example number. Example 5.5, they give you the given mass of the buck is 25 kilograms. They give you the force is 6 Newton. The distance is 0.5 meter. V0 is equal to 0. Okay. The kinetic energy is will be mv squared minus half of mvo squared. This here 0, it's half mv squared. V squared is equal to 2k over m, or V is equal to square root 2k over m. Okay. This is all the we call the kinetic energy, or mass versus speed. Mass versus speed. Tells you the same thing as we have subtracted the law of kinetic energy. They are all talking about the work 1, work 2, and so on. You just apply the law here. Like K1 is half the mass times V1 square. K2 half of the mass of V2 squared, and so on. And delta K is K2 minus K1. Just using the calculator. Okay. The same thing that we have, that x u, the potential energy of a spring. Let us talk about the potential energy first before we go to the spring as here, but what's the potential energy? Okay. This is y, or h sometimes, height, okay? And we have a mass here, standing here, m. This m has no movement, then has no kinetic energy, okay? They said the U is the kinetic, the potential energy. Potential energy is, of course, we have here mg, okay, mg times y, okay. Mg is a force, and y is the same. On the horizontal scale we say fx, but on the vertical scale we say sy. The same thing is in joule, because this is Newton meter, will be joule. Okay. Mass is constant, g also is constant, then the variable is y. This is the variable. The variable which is y. And we say conservation of energy. What's the conservation of energy? That there is no energy loss. If we lose from the potential energy, okay, we gain kinetic energy. Then the energy is the potential energy plus the kinetic energy. Okay? In this case here, E is mgy plus k, and k in this case is 0. There is no kinetic energy while it's here. Okay? It's standing, rest on the top of this building or whatever. Then the total energy now is the mgy plus 0. If this goes down, okay, for example, quarter of y, then we said this is mgy is equal to mg y minus quarter of y plus half of m v square. Let's see here. Okay, this is the total energy we take it from here. Okay, now if we say to take all the m in here, okay, and we'll take the y in here and half of v. They actually will have only y. Okay. Let's take example. Okay, or y minus y naught. It's better to make the first y naught. And the work is F delta y. And here say mg mg. F is mg, and y is y minus y0, okay, which is mgy minus mgy0, and this here W, or work and energy, delta delta U, which is U minus U0. Okay, we'll see what's going on when we drop something from a certain height to the ground. Okay, let me put the same example or the same picture. It's better because you have in the book. Okay. Okay, this can of drink, and we measure from half of this, the middle of, and we call this is the height is y, and here we call y0. Okay. Y here is the mgy, and work is y minus y naught, or mg delta y, the difference between these two heights. This is the same m, this is m and this is m. And here is u0 is equal to mg y0. Okay? And from here to here is the delta y. Okay. They give you the SI unit of energy, which is joule, Newton meter, called joule. Okay, and we'll have example. Example of here that we solved this problem before. The one who's throwing the ball upward, and you will have some problems together, but because the time is running, we have to okay. The y maximum, okay, is equal to v0 square over 2g. We talk this in free fall. Okay, has nothing to do with this, but we have the example in page 141. We have U2 and we have U2 here. U2 is mgy. U2 in this case to mgy. What happened? The first to the left here, it measures the y from y0 from the middle, as you see y0 here. While the y0 here is twice. Okay? Then, not to be confused, like that. Okay? And this one is this. To measure y from here, this is y0, and this is y, and that's that y2 is twice the y here. This is the y0, and this is here the y. These distances or elevations are the same. As we say here, this is 1, and u2 here is equal to mg1y. And here is 2y, like that, mg2y. That's why they give you the 2mgy. Okay. And we have also the conservation of energy. The conservation of energy, okay, like this is to say to mgy, which is potential energy, and here is all here, while kinetic energy is 0. This is the case here, the m here is potential, the energy is energy, all potential energy plus kinetic energy. Here, E in this case is only potential energy. Only potential energy. In this case here, mgy, okay, plus kinetic energy. In this case, this is 0 because y is equal to 0. Okay, here y is maximum. Okay, maximum. Then it's only kinetic energy. In between here, energy is potential energy plus kinetic energy. If you lose here 25%, okay, then you gain 25%. Okay? In the middle, 50%, the E is equal to half of potential energy plus half of kinetic energy, and so on. We say here, say the kinetic energy. Kinetic energy in the first here is equal to the kinetic energy plus U here, okay? Then we say it's the kinetic energy is mv square, okay, plus U is equal to half of m square plus U0. Not too confused. And here, this is the U0. And this is the U. While here is K0 and here K. This is the starting potential energy, okay? And this is the end of kinetic energy. The same thing here, we have the kinetic energy, starting the kinetic energy, and this is the kinetic energy. And this figure here is equal to this. We'll give examples. First of all, here, which is U0 plus K0. The same thing we say at painter, and the craft world drops 1 kilogram, and then M is 1.5 kilograms, okay? And the from a height, this Y is equal to 6 meters, okay? Maybe brush or so. It's 1.5 kilograms, and it drops down here, okay? What is the kinetic energy of the can? It's a can. Can is علبة متاع الزواج. What's the kinetic energy? What's the kinetic energy of the can when the can is at a height of 4 meters? الكان هنا at height of 4 meters. It's asking for the kinetic energy in this case. Okay? First of all, we have the energy here is equal to U0 plus K0. Energy is equal to, by the way, in the book they said it's the kinetic energy plus potential energy. It's okay, the same thing. The kinetic energy here, there is no kinetic energy. The can is standing there. Then kinetic energy is 0 and potential energy is mgy. That will give you m, say 1.5 times 9.8 times 4. Okay? The can is here, then it's 4 meter height. Okay? Okay, here they say the kinetic energy is 8. Sorry, this is 6 meters all. This is the O is at 6 meters. Okay, at 6 meters, which is I don't have the calculator with me, but it's 8.2 joule. And this is the total energy here. The energy at the top here is 8.2 joule. Okay? Now the kinetic energy is the E. I have to clean this, please. The energy, okay, is equal to K plus U at any level. This here is 8.2. It's equal to, this is wanted, and the U at 4 meters, mgy. 8 minus 2 is equal to K plus 1.5, 9.8 times 4. This figure here, with the calculator, it's I don't know, but K is equal to 8.2 minus what's resulting here. Okay, that will give you 29.4 joule. Okay. Next, they asking for the velocity. With what speed will the can hit the ground? Hits the ground, that means it's all kinetic energy. Okay? This is maximum, which is E is equal to U, in this case, is 0. Because it's here. The Y is 0. The Y is 0. Then all the mg U is equal to mg times 0, which is 0 here. Then K is equal to 8.2 joule at this level here. Okay? And K is equal to half mv squared. Okay? Then V is equal to square root, we said, of 2k over m, which is 2 times 8.2, 1.5. Okay. Okay, this is the kinetic energy and the potential energy. Let me summarize this lecture like this here. This is here the potential energy again and the kinetic energy here. In this case here, K0 is equal to 0. Then E is equal to the potential energy only. And this position. In this position here, while this is Y, and this U and K. E is equal to U plus K. U in this case here, because mg Y, which is Y now 0. This is 0 and this is Y. Okay. Then U is 0. Potential energy is only kinetic energy. The potential energy is mgy, and the kinetic energy is half mv squared. Okay. If we say delta K is equal to delta U, because the energy you lose from the potential energy is gained by the kinetic energy. And we have here, it's half mv squared is equal to mgy. And m goes with m, and v squared is equal to gy, and v is equal to square root of 2gy. Okay? Now, the velocity of a dropped body or mass depends only on y. There's no mass. And you see in the TV, when they drop different things, they come to the ground in the same time. Whatever this is heavier, more mass than this, and M1 and M2 and M3, they drop in the same time because the mass has nothing to do with the velocity. Here, this is very important. This is very important. And we have seen many accidents that some pilot رصاصة تنزل من فوق. فكل ما ارتفعت الرصاصة كل ما تنزل كانت قاتلة. حتكون بسرعة أكبر لأنها كل ما ترتفع واجد. لكن لو رصاصة هنا وطاحت بهالشكل مش حدير حاجة. لكن الناس اللي يطلقوا في الرصاص في الهواء يتقوا الله لأن تنزل بسرعة كبيرة بكر. كل ما ارتفعت وايد تنزل بسرعة كبيرة بكر. Okay. The same thing we say the total energy is equal to K0. You find all the examples they use the same equations. Has nothing to do with that, but they change the mass, they change the elevation. That's it. But you have to apply the law as it is. The equation says U is mgy, K is half mv squared. That's it. Whatever they change, okay. Okay. Power. What's power? Power is a work at a certain time. And we say here, power. Okay? And they put the power in that because it's a vector quantity. It is the work done in a certain time. Work done in a certain time. If somebody can do the work in less time, he has a good power. But if the time is big, greater than the other one, we compare with the time. Because power, okay, is proportional with the inverse of the time. And we have the work, as we say, it's Fx over t, okay? And we say Fx over t is velocity, okay? Average velocity, of course, as we said before. And F could be inclined like that. F. And then we say F cosine theta. Okay? But it's not every time that you find F cosine theta, or F you take then F cosine theta, no. If F makes with the horizontal theta, then this here F cosine theta. And the one, because it's in the direction of x. Okay, if this case here, then F is F cosine theta V, average. Also, the power could be work, say, over time, which is F d, distance or displacement, over time, or mgy over time, whatever. Okay. The SI units of P is horsepower. Here is horsepower. Horse HP. Also we call P also watt. W. W not work. The W is watt. Okay. And we have in watt and we have kilowatt. And this is very important, the watt here. Okay. Because we'll see in the other examples for medical use what we do with the watt. The same thing here. We say power is equal to work over T, and T is work over power, or FD over T over power here, okay, or mg d or y over power, same thing, g y over power, whatever here, dx, okay, mg whatever for the work here, okay, x the power. It's just the distance of that. Also we have the efficiency. Efficiency is unitless. Why? Because it's efficiency. Efficiency, we give this epsilon. Okay? Epsilon is the work out, and the energy in, times 100%. It's joule over joule, okay, which is unitless. Okay. For example, if a machine has 100 joule energy input and a 40 joule work output, then the efficiency of this machine is work out and energy in. I'll explain this in Arabic or Libyan accent. أنت تعلق مثلا مضخة في الضي، معناها أنت بتعطي انرجي، بتعطي طاقة اللي هي المضخة، والمضخة تدير لك شغل. إذا تعطيك شغل، أنت بتعطيها طاقة، هي بتعطيك شغل، يعني energy in work out. هذه الافشنسي بتاع الماشين. يقول لك ماشين هذه، يقول لك كويسة، لا هذه مش كويسة، أوكي؟ إذا هذه الافشنسي. واحدة تعطيها نفس الكهرباء، تعطيك مثلا المضخة بتاع نص انش، تعطيك أقل كمية من المية. تعطي نفس المضخة نتاع واحد حصان تعطيك مية أكثر. إذا الافشنسي نتاعها أكثر، لأن الافشنسي تتعامل مع efficiency مع الورك اوت لما تكون الانرجي ان كونستانت. او درت لكم مثال مضخه نص انش ومضخه واحد مضخه نص حصان ومضخه واحد حصان، وتعطيه نفس الضي، وحده تعطيك اقل ووحده تعطيك اكثر. اللي تعطيك اكثر الافشنسي نتاعها اقوى. وكذلك حتى لما تاخذ تشري حاجه من المحلات، الحاجات الالكترونيه ولا الحاجات بتاع تستخدموا فيها في المطبخ ولا او في الترابونوات ولا حاجه، هن نفس الانرجي تعطين ان، بس وحده تعطيك اقوى وشغل اكثر، والاخرى وحده تعطيك شغل اقل. Also, an efficiency of 40.4, which is 40%, means that the 60% energy input is lost because of the friction. الافشنسي عندك 40% فقط، عندك 40%، الافشنسي بتاعها 40%. إذا ال 60% فقدت فيش؟ ممكن تفقد في احتكاك، ممكن تفقد في حرارة، ممكن تفقد في حاجات هذين. إذا هذه الافشنسي. كم الافشنسي نتاع الماشين اللي نبي نشريها؟ وهذا طبعا بالنسبة حتى لطلبة الطب، عندك لما تبي تشتري ماشين تبي تعرف الافشنسي نتاعها كم. المهندس لما يبي يشتري آلة يشتغل بها يبي يعرف الافشنسي نتاعها كم. هل هي تفقد في طاقة حرارية أو طاقة مثلا احتكاك ولا طاقة كذا؟ إذا الافشنسي مهمة جدا في اللازم. كيف ما قلنا efficiency انت بتعطي حاجة مثلا نعطي اللمبة هذه مثلا نعطيها نفس الضي نتاع لمبة أخرى، وحدة الاقتصادية نحن نقولوا ما تفقدش بالحرارة، العادية تلقاها حرارة ساخنة، لفقدت الافشنسي بتاعها أقل. اوكي. لو نمشي نفس العملية مع الكتاب نلقى نفس the same application of the power, of the energy, of the work. The work is different in kinetic energy. We move on the sliding MS as in page 155. اوكي. فنشوفوا نحن شن نختصروا الحاجات اللي خذيناها كلهن. خذينا الورك، وخذينا الكايناتيك انرجي، خذينا البوتنشال انرجي، خذينا الباور، بوتنشال انرجي وكايناتيك انرجي والورك والباور والافشنسي. Okay, then you say potential energy is mgy. Kinetic energy is half mv square. Work is fd and we said the power is work over time, and we have the efficiency is work out energy in.